It's a very long title for a talk, and it's full of buzzwords. And I would like to know how many of you has ever used IPFS? Just one. And DAT? And Ethereum? Okay, a bit more, a bunch more. So every time I read an article or see a talk about decentralized something or peer-to-peer networks, most of the time I encounter a picture, which is this one. So I don't know how many of you have encountered this picture reading things. And there is nothing wrong with this picture, aside the fact that was published the first time in 1964. So things has changed a lot since then, a bit, I would say. And so let me introduce my very own personal and opinionated timeline of the internet. And if you want to play with me, you can raise your hand when I introduce a technology that was invented just after, slightly after you were born. So I have to say that I was not yet born when ARPANET was invented. And okay, one, oh my God, fine. I'm not alone, because the next one I'm in, yes, of course. And the ARPANET was huge. I mean, it was a very resilient network meant to be resilient against a nuclear strike. So it was actually a very distributed network and was the foundation of the internet we know nowadays. And yes, TCP/IP. Yes, I was in, yeah. No, not yet. And okay, one of the building blocks of the internet we know on top of the IP protocol, so a reliable order and error checked protocol. And then there was Usenet. Usenet, okay, one, two, fine. So Usenet was actually the first self-organized decentralized service that enabled people around the globe to send messages and files and so on. It was very interesting because it was able to work also in disconnected network. Before there was an undersea cable that connected Australia to USA, they used to send a bunch of tapes now and then to Australia in order to keep them synchronized with the messages going on US universities. And they arrived, I don't remember if Melbourne, in Sydney, they loaded them inside a server, and then they propagate across Australia as well. So they were able to keep updated two continents, not always connected. And Usenet is still used, I mean, with a slightly different use case nowadays, but was the very first interesting self-organized service. And then in 1984, 1, 2, 3, yeah. Okay, they're starting. So IP were useful, but they were not human-friendly. So we invented DNS, domain name services, and we introduced a bit of hierarchy in a distributed system. So the internet, from a DNS point of view, was not fully distributed, distributed, yes, was decentralized. You have to maintain an organization that is in charge of ensuring that when you ask for a domain, you receive the right response, the right IP. And of course, where there is a sort of centralization, then comes attacks, you know, DNS poisoning and so on. So, but it took up to the 90 to have the very first web page. It was static. And I remember it, actually. I used Mosaic at the time. And it took almost 3 years to have a more dynamic web. So in 1990, we started a static web revolution. In 1993, we started the dynamic revolution, the dynamic web revolution. And slightly after MySQL was invented, it was the database for the internet. Everybody who wanted to build a dynamic website used a combination of those technology and the ones that were after. And in 2000, Napster arrived. And it was the proof that it was possible, again, to have a peer-to-peer worldwide network Not completely distributed, and that's why they were able to block it, actually, because the use case was not so legal, but it proved that the worldwide peer-to-peer network was feasible. And then, in 2004, Amazon had this great idea. So the websites were becoming more complex. You have to build many web servers. You have to balance them. You have to build infrastructure and so on. Why not to offer Elastic WMS infrastructure as service? Of course, they started in 2004, and then they grow, as you know. Okay, but was the very first idea. So if you want to publish an HTML page in 1990, you have to set up your web server, your connectivity, and so on. And as long as things got more complicated, AWS was quite a good answer. And then, shortly after, 5 years after, we had Bitcoin. And we have this incredible functioning technology that combined together a lot of interesting things that happened before in a way that was feasible and actually working. And it was, again, completely distributed, a trustless peer-to-peer payment network, and a bit more. But the internet was slow. The website was slow. People asked for pages and pages and pages, and so that Node.js arrived, and with them the asynchronous web revolution. So we moved from static page to dynamic page to asynchronous web pages, and Akka just shortly after. Okay, so we have an incredible, we had incredible architecture. We have AWS and all the other providers that tried to simplify the life of developers, and we had an incredible capability on serving pages as well. And someone, after Bitcoin, thought, but why in a trusted peer-to-peer network, we should not have also a trusted peer-to-peer naming service? Why we have to rely on a hierarchical and distributed name server like DNS? And so Namecoin was invented on top of Bitcoin, and then on a slightly different blockchain. And then, in 2013, the DAT project was started. And again, the point was, why not to build not only a blockchain? You can't put everything inside a blockchain. The size inside the blockchain is limited. But why don't build a new peer-to-peer network based on the lesson we learned from Napster, BitTorrent, and so on, in order to enable a trustless, pure peer-to-peer network? So that was born. And then Blockstack, the same idea. Why don't build a pure peer-to-peer network for dApps, in order to make it easy to distribute dApps and make them work? And then IPFS, which is another way of distributing peer-to-peer things in a network. And then in 2015, we have AWS LAMBDA, which is huge. Now, not only you can do with just a few configuration files a complete complex architecture, but you can also execute code in the same way, in a serverless fashion. You don't have to worry about anything else. Just execute your code, as long as you pay, of course. And then, just 1 year after, the Ethereum movement started. All the Ethereum things started. So, thinking and trying to bring the blockchain technologies to a distributed VM system in order capable of executing code in a trustless environment. And so we have also BigchainDB, which started again to try to replicate the success of MySQL, but in a very different way. So the database for the blockchain era, and so on. And so here we are today. And the question is, okay, we started with a very distributed and decentralized internet, and we are ending up with a bit more centralized internet again. Last year, 70% of the internet traffic was through Google and Facebook. And nowadays, AWS is an incredible service, but we are giving in the hands on Amazon all our activities, all the things that we develop. So the point is, are we able to build for the next generation, like the ones that build TCP/IP, ARPANET, and all the technology that enable us today to do what we do? Are we able to enable the next generation of programmers not to be locked in a centralized internet? So that's the real question. And in order to understand this in a distributed world, I mean, we need to rethink a bit the way we classify the networks. So it's not a matter of having a distributed or decentralized or a centralized network. We need to talk about distributed and decentralized networks and how they are truly distributed or not. For example, Bitcoin is a pure peer-to-peer network. There is no entity who decide the rules, who can change the rules of the network. You have to establish consensus among the miners, the developers, the users, in order to change the rules. Ethereum, on the other hand, we can debate. I mean, there is a foundation that can change the rules and issue a hard fork. So if you think that the foundation is not evil, is a peer-to-peer network with a facilitator. Or if the Ethereum Foundation becomes evil, will be a peer-to-peer network in a hybrid peer-to-peer network. So every time we talk about peer-to-peer, we need to understand what we are talking about, which kind of service we are looking at. So how we can change things. This is a classical picture from Amazon. So if you want to build this completely serverless application today, you can use S3 as a storage for your single-page application or other things. You can use the API gateway and the LAMBDA to trigger the business logic of your application and build a completely serverless application stack. So how we can change this? We need to change this starting from the place where we store the application. So let's take a step back. How works a static website? So it's simple. You have a client, you have a server. You issue a request to the server, you get back a request. That was the internet in 1990. Then things got more complicated. You need more web server. But even if you have more web server with a balancer, at the end, a single request is answered by a single web server. You can make things more complicated, add regions, whatever you want. But at the end, a request is answered by a single server at the end. So how we can enable peer-to-peer serverless computing? We can start substituting, changing S3 with another component, IPFS. Okay, IPFS is an acronym that means Interplanetary File System, and it's not a joke. The stars are actually in the program, in the sense that one of the idea was that how we can cope with very problematic networks. Let's imagine that we go to Mars. The communication between the Earth and Mars will be quite challenging. And we have not to go to Mars to have such difficult conditions. You can go to whatever developing country nowadays. You can go to Africa. Electricity is not always on. The networks are not so reliable. So we are living in a free and happy network here, but things are more complicated. So the idea with IPFS is that we can build and things in a slightly different way. Let's start with a quite equivalent picture from a static website. So let's say that you have a static website and you want to publish on IPFS. What happens is that if you have a browser, you issue an HTTP request to a gateway, no matter what is the gateway, and the gateway talks with the peer-to-peer network. And so what happens is that each node that has the content you're asking for can give back a block of the content in a pure and truly peer-to-peer fashion, like BitTorrent, okay? Because each file is sliced into equal-sized blocks, and the whole network can respond together to a single request. Of course, you have a bottleneck here, the gateway. But the point is that it doesn't care how much bandwidth do you have between the nodes. The bandwidth in this case will be the bandwidth available for the gateway, because each node, no matter which kind of connectivity they have, just respond with a block. The more the nodes, the faster the response. Of course, and you get back the information. And of course, if instead of a browser, you use the IPFS client, you got the same result directly on the client. So all the nodes will respond with a block, each one, more than one, it depends, to the client itself. So again, in this case, the broadband is the broadband of the client. That's a huge revolution if you think. Nowadays, we see everywhere, everybody asking for more bandwidth, everywhere. But the real point is that we need more bandwidth because we distribute information like we distribute water. We have very big basins. We need very huge tubes to push the water from the very big basins to the house where we need them. So with technologies like IPFS and other peer-to-peer ones, we can completely change the paradigm. Okay. So let's do a bit of demo. So it's very easy to install IPFS. It's based on Go. There is also a JavaScript implementation you can run inside the browser. Okay. And let's try to understand what makes IPFS different. So, okay, let's say that we want to build, a very complex website. Can you see it? No, sorry. There is a problem here. Let's see. Okay. Let's say that we have this very, very complex website. And I can change the resolution a bit. Just a second. Okay. So we have this very complex page. Okay. And let me take, there is something wrong with the multiple screen I have. Just a second. Okay. Okay. So I already installed IPFS on my computer. Let's say that we want to, when you install IPFS, you have to issue IPFS init. It's like a git init. So it creates a folder inside your home folder. And it's the place where you add things. So in this case, we have a file here that we want to add to IPFS. Okay? So if I issue an IPFS add, what happens is that, can you see it? Okay. What happens is that it adds the content to the IPFS folder and gives you back an hash. This is the hash of the content. So that's why IPFS and DAT, for example, are called content-addressed file systems. So you don't have paths. You just have hashes. Okay. And this hash identifies in the whole network this kind of web page. So it's quite simple, the web page we have done so far. So it's very static and so on. The other interesting thing is that actually IPFS creates a Merkle tree. So if I ask, OK, add the whole folder, what happens is that we have the same hash, as you can see, for the file, but we have a new hash, which is the hash for the folder. Okay. So what we can do with these hashes? Okay, we can ask, for example, a gateway. Sorry, but I need to switch back to my screens. I had prepared another thing, but OK. OK, so where is the gateway? The point is, where is the node? So the actual question is, OK, now I have added to my local repository a file. But who can see it? Nobody. I have to at least fire up one single node. OK, so now I'm starting up a server, a daemon, inside my computer, which is capable of serving the file I have added to the repository. And the interesting thing now is that I have, for free, an HTTP gateway as well. So if I ask for this hash, OK, here we have. I have a web page. OK? The important thing now is that I have a node that serves this hash. But if I ask another gateway, please retrieve the same hash, after some time, the gateway will respond with the same content. What happens in the background is that if I ask a gateway for an hash, it asks the peer-to-peer network, is there anybody who has this hash? How many of you? And it starts asking blocks from each of them. So it's very different from a web server. In a web server, in a URL done for HTTP, the content is linked to the server who provides the content as well. So the full URL is needed in order to access the content. If the domain is poisoned, if the server goes down, nobody else can provide you the same content. In the IPFS world, instead, as long as there is at least one node that has in the cache or stored permanently in his cache the content, you will be able to access it. So that's a specific use case. But for example, when the Turkish government decided to shut down the Turkish version of Wikipedia, IPFS folk were able to translate, to port the Wikipedia to IPFS and make it already again available to the Turkish people. So think about it. So we can see also another thing. So OK, let's go a bit more complex. Let's say that you have, you want to add links, because what is a website without links? OK, so in this case, I have a website which has a folder inside and a link between. OK, so if I say add this guy, as you can see, a new Merkle tree is built. OK, so you have an hash for each element. That means that you can access both the root element or each one inside. So for example, if I take this element and go to my browser, I got the new website. And I got also a relative link, which is working. And that's the other interesting thing. So the HTTP gateway is smart enough to understand relative links. And that's a problem if you build complex things in IPFS. But the point is that you can access the content inside a Merkle tree, specifying the root of the Merkle tree and the names of the object inside. Or you can access exactly the same content. So this content, for example, is identified by this hash. So if I replace the whole path with just the hash, I again get the same content. And that brings us to the third thing. So I can build also websites with internal links pointing to hashes. So this is a fake relative link. So if you ask an HTTP gateway, IPFS HTTP gateway, such a link, it resolves it to the original content. So let's do it. So we have the third guys here. Okay, so we have a website which has a link inside pointing to another Merkle tree. Okay? And we can go there, ask for the root, okay, and access a link that points to an hash. The point is why you need such a complex thing. Hashes are not so fine to read and so on. Let's imagine that you have an external dependency, a JavaScript library. I don't know if you remember, I will go to in a moment in the slides. So if you have an external library, a specific version of a library. Nowadays, you have to, we have to go too faster. You have to hope that the maintainer of the library keeps the library in the same place. But if you can get the library, store inside the IPFS, you can access the hash. You can store the hash locally, so you make your library available to others as well, and you are sure that nobody can change the content of the library, change the version of the library, because if you change the content of the file, the hash changes. Okay. And of course, nowadays they have also built, hopefully, a new component, which was released last month. So you can have an add-on for Chrome and Firefox that starts also a local IPFS node in the browser, if you want, or access the actual node you have on the server. And what enabled this? This changed things in a very interesting way. So what happens is that, thanks to this, okay, you have all the communication in the peer-to-peer fashion done inside the browser. So the IPFS web companion actually talks directly to the peer-to-peer networks. And in this way, you avoid the bottleneck of a typical gateway, external gateway. Very interesting. We don't have so much time, so I need to go faster. So the other point is that, what about if you want to publish a content that changes in times? So the point is that you can't use IPFS, in the sense that every time you change the content, you publish a new Merkle tree. There is a trick here. There is another protocol which is called IPFN, which enables you to link a stable hash, which represents a node actually, to a specific Merkle tree. In this way, you can publish an hash that never changes, and when you change the content and you publish a new hash, you just have to issue a command saying, okay, link this hash of the node to the hash of the content. And if you want to go a bit down this path, I mean, I think you could take a look also at the DAT project, which is very interesting. It started with a completely different use case from universities. So let's imagine that you want to distribute huge data sets of data across universities. And you want to be able to update those data sets. And you want to be able, those universities, to synchronize those data sets. So the DAT project is all about this. Use another kind of technology, always peer-to-peer. Take a look. It's very easy to install. It's an NPM model, so there is no point about it. And you can also try out a browser which natively supports that protocol. So I can give you just a quick demo. So let's say that I want also to, okay. So for example, this is a static version of my blog. So it's a quite simple, website, okay? And let's say that we want to publish with that. Okay, we issue .share. Okay, and now we have a new hash here. I can take this hash. Actually, I can take the complete hash here. and go to, sorry, to Beaker, once I got it, okay. Paste, and now here I am. I have a complete DAT published node, and I can have links and so on. So why it's interesting, all those things? Why are they interesting, all those things? Because, for example, let me switch back to the presentation. Okay. You can build on top of that the DAT installer for mobile application. This is a very interesting project that enables installation of, mobile apps between mobile phones without a store. So there are use cases, very interesting use cases. Think about developing countries where you don't have access to networks or you want to distribute things to people. There are very interesting projects around it. So you just have to install on one phone your application, mobile application, and if there is another phone on the same Wi-Fi network, you can share the DAT address and install the application on the other mobile phone as well. So we can also overcome the limit that we have now with stores and without doing illegal things as well. Okay, so just to finish this part and going to the end of the talk, why we need those things. I don't know if you remember the left pad crisis. Okay, so a developer unpublished all the open source project that he has done due to a legal dispute on one of them, and suddenly all the websites that were continuously building things based on the left pad, which was a very simple function, just give the left part of a string, crashed because there was no left pad available anymore. So such kind of thing shouldn't happen in the open source world as well. Okay, and then we can use IPFS and DAT to overcome this kind of thing. So why use them? Because bandwidth cost is on the client, not on the server. The peer-to-peer network is self-organizing, is able to work in disconnected networks as well. And the content is resilient to DNS, poisoning, or censorship. And that's a huge thing. So let's go through the end of the thing. So we can remove and substitute with IPFS and DAT the S3 storage system. But what about the rest? So we can try to explore Ethereum. And of course, let me say, you can't switch AWS Lambda tomorrow morning with Ethereum. Okay? So when you try to download Ethereum from the website, that's the warning you have. And that's fine. And so in this scenario, you can use Ethereum as your backend. But there is an issue. Yes, of course, you can build smart contracts. There are sort of functionless, serverless functions. But you can't store everything inside a blockchain. The size is limited. So linking together technology like IPFS to the blockchain, you can use blockchain to store relevant information. And IPFS links to, for example, you can store inside the blockchain hashes that points to content inside IPFS. And if you want, you can try out, for example, this framework, which is EmbarkJS, which enables you to do such a thing. So it combines you the Ethereum smart contracts with the IPFS world, and you can write and read from IPFS, issue contracts in Ethereum, and so on. It's quite easy to install. You have to install Ethereum. You have to install an NPM module, which is Embark. And then you have to configure your IPFS in order to support CORS if you want to do local debugging. And I think we are almost done. So I had a demo, but I can show you. But I would like to show you one last thing, which is this guy. This is an open source project. Unfortunately, it's not compatible with the latest version of Ethereum and Embark, but I'm working on a fork of this just for a demonstration. So I think in the Next week, you will find my fork. And in this case, what this application does, it's a mix. So it accesses the Google Maps API and enables you to store your own photo on your own IPFS node and store on the Ethereum through smart contracts the information about which photos belongs to who. So you have inside the smart contracts and inside Ethereum the relevant information. These are my photos. So these IPFS hashes are linked to my wallet in Ethereum. And so the application is completely serverless. So you can load it from whatever you want, IPFS, DAT. And once it's loaded, it triggers smart contracts to retrieve the information about where are and what are my photos, and you can browse them by tags and so on. So that's kind of thing I would like you to resonate in your mind. So when you will develop your new best idea, your new best project, think about it. Do you want to add a brick to the wall in the centralized internet? Do you want to add a brick in the building of a new decentralized and distributed internet? Okay. Just one last thing. We are publishing the new Tech Radar if you want to follow us. And of course, we are in Italy. So that's the time for questions. Thank you very much.
Hello.
Hi.
Alessandro, thank you for your talk. I have a question about the hashes. So I think you mentioned that hashes are based on the content of the file, right?
Yeah.
The generated ones. So my question is how we can build linkage between the files if they are changed. The link should change. That means, the hash will change. That means we cannot really hard code the hashes inside our HTML because they will keep changing. So how we can build really a system which you can be linked between each other?
So
Thanks.
the real question is this technology suitable for everything? The answer is not. The short answer is not. So it's better to store links that points to hashes for content that you need to be sure to be present and that you want to be very specific. So assets, for example, are fine. Of course, you don't have to translate to hashes all the links you have in your website. You have to build a mix of them. For example, there is a local application which, together with the IPFS node, there is a browser that enables you to understand what's going on. And it's a quite standard HTML application stored inside IPFS node. So you can use it disconnected from the network. And if you look inside the application, you will find some resources that are pointed by hash and the other not. So it depends. Of course, the other answer, a bit more complex, is that you can use IPFN. So in this way, you have to link at the hash of a node manually to the hash of a link, a sort of auto-publish DNS. Okay, it's not really working nowadays. It's quite slow. So there are plenty of other things you can do. For example, you can publish your hash through Namecoin or inside your DNS TXT entry. So in order to make easier for people to access your changing content. But the mindset you have to keep in mind is that IPFS is meant to be used to store things for eternity. So, of course, you can store different versions of things. That gives you another answer. So it doesn't give you two levels. In IPFS, you have the IPFS layer and the IPFN layer. In that, you have just one layer that answers your question. So you have an hash, which is a sort of combination of the content and the node. And so you just publish one hash. And if you change the content, what happens is that you have an append-only log to the content. So it's a bit more trickier. Of course, in this way, you are introducing less resilience, because once you have an hash linked to a node, only the person on this node can publish a change. Okay, so there is many people can synchronize and read, but just one person can write.
Clear, thanks.
Okay. There is a question there.
Hi, and thanks for your talk. Really, really inspiring. I'm curious about a detail where you were showing those files being sliced, and then we make a request, and each node contributes back to the response with maybe one chunk or something. I'm curious how the issue of overhead has been solved. Many responses, lots of overhead.
Okay, the answer is twofold. First of all, there is a responsibility of each single node in not responding in a fake manner. So if a node starts to fake responses, is take apart from the network. So actually what happens is that each node creates its own peer-to-peer map of available peers. So we don't have time, but if you access the local application, shows you the world map with the peers that are connecting to your node. And also, when you use the web companion, you see how many peers are connected. So, of course, you are not connecting to all the peers in the world. You are connecting with the peers that are visible to the topology you are building at the moment. So, the point about the overhead is not completely solved at the moment, in the sense that, okay, this is an experimental network. It's working fine almost all the time. At the moment, there are problems with HTTP gateways. So I've seen by experience that if you access with the client directly to the network, you have good response time. If you access through instead a gateway, for example, the official gateway, things get a bit weird because the peers maintained by the gateway are huge, and so the response time is huge. So, I mean, it's an evolving technology, yes. I don't know if it's answered your question. Okay. Any other question? There?
Hi, thanks for the talk. The question is more about how IPFS solves the problem of censorship, because I think it's a hot topic in this kind of systems.
Absolutely. So the point is that, I mean, IPFS does no magic. So if you want to avoid censorship, you have to at least have a bunch of nodes that serve the same content. Okay. And if someone tries to shut down a node, you can in a very fast way build up a new node as well. So the point is that for a censor to shut down all the nodes is quite complex. The more you have, the more hard is it. Okay, so the real question is that you can't shut down the node like you do with the DNS or with web servers. At the moment, there is no incentives to build such a network. That's why the creator of IPFS are now building Filecoin, which is an incentive network. So you have coins if you store content of someone else, if you make available your bandwidth, your storage, and so on. So at the moment, it's a voluntary network. So you can publish things and ask other people to pin things. That's what happened with the Turkish Wikipedia. Fine. If you have other questions, we can talk aside. Okay. Thank you.